Welcome to these gentle, soothing stories for sleep. I'm so glad you are here. Whether you are preparing to drift off to sleep, relaxing after a long day, or simply seeking a quiet companion, you've come to the right place. Tonight, we will embark on a journey to explore the final frontier, to ask ourselves, in this vast and ancient cosmos, how far have we really gone? Before we begin, I'd love to know where you're listening from tonight, or how your day was. Please leave a comment below. Wherever you are, I hope you are feeling comfortable, relaxed, and ready to explore something gentle yet extraordinary. And if you find these soothing scientific journeys interesting, or pleasant, or even just wonderfully weird, please consider liking this video and subscribing to the channel. It helps more souls who are searching for peace find their way here. Let us begin by imagining, just for a moment, that you are floating. There is no up, no down, only a profound and perfect silence that seems to press in on you, not with weight, but with its complete and total absence. You are adrift in a velvet blackness so pure it feels like a substance, a soft and endless ocean. All around you, the stars are not the gentle twinkling lights you know from home. Here, they are sharp, unwavering points of diamond fire, fixed in their celestial positions. And then, you turn, and you see it. It is not the grand, swirling marble of blue and white that you expect. From this impossible distance, it is just a tiny point of light, a single pixel of pale, unassuming blue, almost lost in the vastness. It is small enough to be blotted out by your thumb, held at arm's length. This is your home. This is Earth. And in that single, solitary point of light, every person you have ever loved, every hero and coward, every king and peasant, every creator and destroyer of civilization, every mother, father, and hopeful child, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. From here, the borders are invisible, the conflicts are silent, the oceans are a smear of blue, and the continents are an indistinguishable part of the whole. It is just a pale blue dot. This breathtaking and humbling perspective was not an accident. It was a deliberate act of profound foresight. In the year 1990, the Voyager 1 spacecraft, a robotic emissary from humanity, had completed its primary mission. It had flown past the majestic giants of our solar system, Jupiter and Saturn, and was now hurtling towards the unknown darkness of interstellar space. It was already a staggering 6 billion kilometers away from home, a distance so large it almost loses meaning. At this point, the mission controllers were planning to shut down its cameras forever to conserve power for the long journey ahead. But the astronomer Carl Sagan, a man who possessed a rare gift for seeing the poetry in the cosmos, made a special request. He pleaded with NASA to turn the spacecraft around one last time and take a final picture of its home world. It was a technically difficult maneuver. From that far out, the Earth would be incredibly close to the Sun in the field of view, and the brilliant glare could have easily damaged the camera's sensitive optics. The spacecraft would be taking a picture of a dimly lit speck from the outer darkness. But the team at NASA agreed, and on February 14th, 1990, Voyager 1 pointed its camera back through the solar system and captured the image. It is not a beautiful photograph in the traditional sense. It is grainy, and the Earth is less than a single pixel in size. But its emotional and philosophical power is immeasurable. It is a family portrait of us all. To truly grasp the distance from which this portrait was taken, we need a better yardstick than kilometers or miles, numbers which quickly become too cumbersome for the cosmic scale. Astronomers use a measurement called the astronomical unit, or AU. One astronomical unit is simply the average distance from the Earth to the Sun, which is about 150 million kilometers. It's a wonderfully simple and relatable measure. If you are 1 AU away from the Sun, you are at home. When Voyager 1 took the pale blue dot photograph, it was approximately 40 astronomical units from the Sun. Imagine our distance to the Sun, that vast gap that light itself takes over 8 minutes to cross, and now multiply that distance by 40. That is where our tiny probe was, looking back at us. It had travelled so far that the Sun itself was just a brilliant, but distant, star. This immense journey and the image it produced gave humanity a unique gift, a taste of a profound psychological shift that until then, only a select few had ever experienced. The overview effect. Astronauts who see the Earth from orbit often describe a sudden, overwhelming feeling of connection to the planet and to all of humanity. Seeing the thin, fragile wisp of our atmosphere, the seamless whole of the planet without borders, they report a cognitive shift, a new understanding of our shared destiny. The pale blue dot picture democratized that experience. It allowed all of us, grounded here on the surface, to see our world as it truly is. A small, fragile stage in a vast cosmic arena. And so we reflect on this single point of light, this lonely speck. It is our only home. In all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The responsibility is ours alone. This distant image of our tiny world is a powerful reminder of our need to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. It is a testament to how far we have gone, sending a piece of ourselves into the outer solar system. And yet, it also reveals how small our beginnings are. That tiny, shimmering dot of light contains everything we have ever been and everything we are. But what lies just beyond its atmospheric veil? What is the very first, invisible step of our journey away from home? The line we must cross to truly enter that final frontier. Imagine the feeling of rising, faster and faster, leaving the world behind. The air, which has been your constant companion for your entire life, begins to thin. You can feel it not as a breeze, but as a lessening of substance, a gradual fading of resistance. And as you climb, the color of the sky above you begins a profound and beautiful transformation. The familiar, friendly powder blue of a summer's day gives way to a deeper, more royal azure. Then, as you continue your ascent, that blue darkens further into a stunning indigo, a color so rich and deep it seems almost unreal. Finally, at the very edge of your vision, that indigo bleeds into the pure, absolute black of the void, a black dotted with those sharp, unblinking stars. Below you, the gentle pull of gravity, the force that has anchored you to the ground since birth, begins to loosen its relentless grip. You feel a growing sense of lightness, of buoyancy, as if you are being lifted out of a deep and invisible ocean. This is the sensation of departure, the feeling of crossing a threshold from the world we know into the one that lies beyond. This journey from blue to black is not just a poetic transition. It has a name and a specific altitude. It is a boundary known as the Kármán line, and it is the internationally recognized border where Earth's atmosphere ends and outer space begins. This line is drawn at an altitude of 100 kilometers, or about 62 miles, straight up from sea level. It is named after Theodor von Kármán, a brilliant Hungarian-American physicist who first calculated its significance. He realized that there is a point as you go higher where the atmosphere becomes so incredibly thin that the principles of flight as we know them simply cease to work. It's not a physical wall, of course. There is no ribbon in the sky to cut through. It is an invisible, conceptual boundary based on a beautiful and simple physical reality. It is the point where the air is no longer enough. To understand why this specific altitude is so important, we have to think about what keeps an airplane in the sky. An airplane flies because of a principle called aerodynamic lift. As the wings of the plane move through the air, their curved shape forces the air to travel faster over the top surface than the bottom. This difference in speed creates a difference in pressure, lower pressure on top, higher pressure on the bottom, and this pressure difference pushes the wing, and thus the entire aircraft, upwards. You can feel a simple version of this yourself. If you hold your flat hand out of the window of a moving car and tilt it slightly upwards, you can feel the air pushing your hand up. The lift you generate depends on two key things: the density of the air and how fast you are moving through it. If you want more lift, you can either go faster or find denser air. Now, imagine you are an airplane pilot trying to fly higher and higher. As you ascend, the air becomes less and less dense. To get the same amount of lift to keep your plane from falling, you have to compensate for the thinning air by increasing your speed. The higher you go, the faster you must fly just to stay aloft. Von Karman calculated that at a certain point, around 100 kilometers up, this relationship reaches a critical limit. To get enough aerodynamic lift from the vanishingly thin air, a vehicle would have to be traveling faster than orbital velocity. In other words, to use your wings, you would already have to be going so fast that you would be in orbit anyway, held up by your speed and the curvature of the Earth, not by the air. At this point, wings become entirely useless. You are no longer flying through the sky, you are flying in space. This invisible line, based on a physical principle, has profound legal and political consequences. It creates a fundamental distinction that governs how nations interact above our heads. Everything below the Karman line is considered national airspace. Just as a country controls its land and its coastal waters, it also controls the column of air directly above its territory. Any foreign aircraft, whether it's a commercial airliner or a military jet, needs permission to enter this sovereign airspace. But the moment a vehicle crosses that 100-kilometer threshold, the rules change completely. It enters outer space, which is considered the province of all humankind. It is an international domain, governed by treaties like the Outer Space Treaty of 1967. No nation can claim sovereignty over any part of it. This means a satellite from one country can legally and peacefully orbit over any other country without permission, so long as it stays above that magical 100-kilometer line. The Karman line is therefore a crucial boundary in international law, a negotiated peace that keeps the orbital highways open to everyone for exploration and discovery. It is a human agreement, an attempt to impose order on the seamless gradient of our planet's atmosphere. We look up at the sky and see a single, continuous expanse, but we have drawn a line upon it, a line that separates the laws of the land from the laws of the cosmos. Is space truly somewhere else, a different place entirely? Or is it simply a continuation of our own world, a place where the air just gets quieter and thinner until it fades away into nothing? We have crossed this invisible line, this first frontier, and we are floating in the silent blackness. But even here, we are not truly free. We are still caught in Earth's powerful and unseen embrace, tethered by the immense chain of gravity. So, how do we break that chain? What does it take to not just visit the edge of our world, but to truly leave it behind forever? Picture yourself standing in an open field on a quiet afternoon, holding a small ball in your hand. You toss it gently into the air, and for a moment, it seems to defy the world, climbing against the sky. But its journey is fleeting. It slows, pauses at its peak, and then inevitably, it returns to your hand. You throw it again, this time with more force. It flies higher, stays aloft for longer, but the result is always the same. It comes back down. Every object you have ever thrown, every bird that has ever taken flight, every leaf that has ever fallen from a tree has been bound by this fundamental rule. What goes up must come down. It is the most basic law of our world, the unseen chain that ties everything to the surface of our planet. So, what would it take to break that rule? What would it take to throw that ball with such impossible, unimaginable force that it would climb and simply never return? This is the fundamental challenge of leaving home. It is the challenge of achieving escape velocity. To feel the true scale of this challenge, imagine yourself standing a safe distance from a rocket launch pad. The air is still, and a colossal tower of metal and fuel stands silent against the sky. Then, the countdown reaches 0. The world erupts. It begins not as a sound, but as a vibration. You feel deep in your chest, a tremor that runs through the very ground beneath your feet. Then comes the roar, a sound so immense it is a physical force, a crushing wave of energy that washes over you. From the base of the rocket, a pillar of incandescent fire bursts forth, a man-made sun that turns the landscape stark white with its brilliance. The rocket strains against its clamps for a moment, gathering its titanic strength, and then it begins to rise. It moves with an impossible slowness at first, as if lifting the weight of the entire world on its shoulders. It is pushing against the immense, invisible mass of the planet's gravity, fighting for every inch of altitude. This is not a gentle ascent. It is a battle, a controlled explosion of unimaginable power, all directed at a single goal: to break the unseen chain and push a tiny capsule full of human hope out of the deep gravity well of our planet. This incredible display of power is all in service of reaching a very specific number. For Earth, that number is approximately 11.2 kilometers per second. That's a little over 40,000 kilometers per hour. This is Earth's escape velocity. Now, it's easy to think of this as a kind of cosmic speed limit, a speed you must be going at the moment you leave the atmosphere. But that's not quite right. Escape velocity is more accurately described as an energy requirement. Think of it this way. Everything in your life is a balance of energy. An object at rest has potential energy, and an object in motion has kinetic energy. When you throw a ball upwards, you give it an initial burst of kinetic energy. As it climbs, gravity works against it, converting that kinetic energy into gravitational potential energy. The ball slows down. When all the kinetic energy is gone, it reaches its highest point and starts to fall, turning that potential energy back into the kinetic energy of motion. It comes back because you didn't give it enough kinetic energy to overcome its total gravitational potential energy. Escape velocity is the point where that balance tips. It is the speed at which an object's kinetic energy is exactly equal to its gravitational potential energy. If you can achieve that speed, you have given your spacecraft enough energy to coast away from Earth forever, even as gravity continues to pull on it, slowing it down over vast distances, but never quite enough to stop it and pull it back. Perhaps the most intuitive way to picture this is to imagine that our planet sits at the bottom of a deep, invisible well. This is Earth's gravity well. The sides of the well are steepest near the planet and become gradually shallower the further away you go. Living on the surface is like being at the very bottom of this well. To get anywhere in space, you have to climb its sides. Launching a rocket into orbit is like firing it up the side of the well, with just enough energy that it doesn't fall back down, but also doesn't escape. It enters a stable path, perpetually circling around the inside of the well, like a marble rolling around the inside of a bowl. But to truly leave, to travel to other planets, you need to give your spacecraft a much more powerful kick. You need to give it enough energy to climb all the way up the steep slope and over the rim of the well, allowing it to roll free into the flatter planes of the solar system. This is what escape velocity represents. The energy needed to climb out of the well. And every celestial body has its own gravity well, of a different size and depth. The Moon's gravity is only 1/6 that of Earth's, so its well is much shallower. Its escape velocity is a much more manageable 2.4 kilometers per second. This is why the Apollo lunar module needed a relatively small rocket to lift off from the Moon and return to orbit. A colossal gas giant like Jupiter, on the other hand, has a gravity well of terrifying depth. Its escape velocity is a staggering 59.5 kilometers per second, more than 5 times that of Earth. Leaving the gravitational grasp of such a world would require an almost inconceivable amount of energy. As we contemplate this immense struggle against gravity, it's hard not to see a reflection of our own lives. We all have our own forms of gravity, our own invisible wells that hold us in place. The comfort of routine, the fear of the unknown, the weight of old habits, these are the forces we must overcome to grow and to change. And in our lives, just as in spaceflight, there is a kind of escape velocity. It is that critical moment of decision, that surge of will and effort required to break free from the patterns that bind us and to set ourselves on a new and unknown trajectory. The universe, it seems, is built upon this fundamental principle of breaking free. Having now expended that colossal energy, we have climbed over the rim of Earth's gravity well. We are adrift in the sun's domain, a tiny vessel in a vast ocean. And out in the darkness, our nearest neighbour awaits, a silent, dusty, and patiently waiting world. How did we first reach out and touch it? Imagine for a moment that you are standing in a world utterly devoid of colour. The ground beneath your feet is a fine, powdery dust, a uniform shade of grey that stretches out to a razor-sharp horizon. You look up, and the sky is not blue, but a profound and star-dusted black. And the stars themselves are different here. They do not twinkle. They are hard, steady points of light, hanging in a silent, eternal night. You turn your head, and the only sound you can perceive is the gentle rhythm of your own breathing, a soft hiss and flow inside your helmet. There is no wind, no rustling leaves, no distant hum of civilization. The silence is so complete, so absolute, that it feels like a presence. And then you see it. Hanging in that black sky is a sight of such breathtaking beauty, it seems almost impossible. It is a swirl of brilliant blue and dazzling white, a living, vibrant jewel suspended in the void. It is the Earth. It is home. This silent, monochrome world is the moon, and this overwhelming, transformative experience is what it was like for the 12 human beings who have had the privilege of walking upon its surface. To step onto the Sea of Tranquility, as Neil Armstrong and Buzz Aldrin did in 1969, was to enter a landscape that was both starkly alien and strangely familiar. The fine lunar soil, or regolith, had the consistency of talcum powder or fine sand, and it clung to everything. The shadows were a phenomenon unlike anything on Earth. With no atmosphere to scatter the sunlight, there was no ambient light. Shadows were not merely dark, they were pools of pure, featureless black. An object was either in the brilliant, direct glare of the sun, or it was in total darkness, with no gentle transition between the two. And hanging above it all was our planet, 4 times larger in the lunar sky than the moon appears in ours. For the Apollo astronauts, this view was a constant and powerful reminder of where they had come from. They were hundreds of thousands of miles from every other human being, standing on an ancient, lifeless world. Yet they could see all of humanity in that single, beautiful sphere. It was a moment of profound connection and profound solitude. Beyond the sheer wonder of the experience, the Apollo missions were a scientific treasure trove. The most precious cargo brought back from these journeys was not the astronauts themselves, but the 382 kilograms of lunar rocks and soil they collected. These were no ordinary rocks. On Earth, our planet's geology is active and chaotic. Wind and water cause erosion, and plate tectonics constantly recycles the crust, melting old rock and forming new. The moon, however, is geologically dead. It is an ancient museum, and the rocks on its surface are pristine artifacts from the dawn of the solar system, preserved for billions of years. Scientists called them Genesis rocks because they provided an unblemished snapshot of the conditions 4.5 billion years ago. By studying their composition and age, we were able to piece together the violent history of our own celestial neighborhood and confirm one of the most important theories about our home, the giant impact hypothesis. The evidence in these rocks strongly suggested that the moon was formed when a Mars-sized object collided with the early Earth, blasting a huge amount of debris into orbit, which then coalesced to form our lunar companion. Walking on the moon was also a lesson in a whole new kind of physics. The moon's gravity is only about 1/6 as strong as Earth's. This meant that a 200-pound astronaut in their full suit would feel as if they weighed just over 30 pounds. This led to a unique and memorable way of moving. It wasn't just about being able to jump much higher. A more subtle and important principle was at play: inertia. While an astronaut's weight was drastically reduced, their mass, the amount of stuff they were made of, remained exactly the same. This means that while it was very easy to push off the ground and bound into the air, it was just as difficult to start moving, stop moving, or change direction as it would be on Earth. This combination of normal inertia and low gravity made walking awkward. The astronauts found the most efficient and stable way to move was a kind of loping bunny hop, a gentle bouncing gait that allowed them to maintain their forward momentum in a controlled way. It was a dance between human physiology and alien gravity. And among the equipment left behind on that dusty surface was an experiment that continues to provide crucial data to this day. The Apollo missions deployed several laser-ranging retroreflector arrays. These are essentially sophisticated mirrors, designed to bounce light directly back to its source. Here on Earth, astronomers at observatories can fire powerful laser beams at these mirrors and measure the precise time it takes for the light to travel to the moon and back. This simple act of timing allows them to measure the distance to the moon with astonishing, millimeter-level precision. These ongoing measurements have taught us that the moon is slowly drifting away from the Earth, at a rate of about 3.8 centimeters per year. They also provide some of the most stringent tests of Albert Einstein's theory of general relativity, confirming its predictions with incredible accuracy. To look back on the moon landing is to look back on a moment of almost unbelievable audacity and brilliance. It was the culmination of the work of 400,000 people, a symphony of engineering, science, and sheer human courage. It required millions of individual parts in the most complex machine ever built to work in perfect harmony. It was an act of profound trust, a moment when humanity, for a brief time, set aside its divisions and worked together to achieve a dream as old as consciousness itself, to reach up and touch the heavens. We touched the moon, our silent, constant companion in the night sky. But other worlds beckon, worlds of fire and storm, of rust-red deserts and crushing toxic clouds. What did we find when we sent our robotic eyes, our tireless electronic proxies, to visit our planetary siblings? Can you imagine what it would be like to hear the very first sound ever recorded on another planet? It would not be a grand, orchestral score or a profound alien message. It would be something far more subtle, far more elemental. It would be the sound of the wind, a faint, ghostly whisper, captured by a tiny microphone on a robotic explorer, a sigh from a world that has been silent for billions of years. This is what we heard from the surface of Mars. A thin, ethereal wind blowing across a desolate, rust-coloured desert under a pale butterscotch sky. It is a sound that travelled over 200 million kilometres of silent space to reach our ears, a lonely greeting from a world of dust and rock. Through our robotic emissaries, we have not only seen other worlds, but we have begun to listen to them as well, and their stories are told in the language of physics, chemistry, and geology. Let us journey now with one of these emissaries, the Perseverance rover, as it trundles across the floor of Jezero crater on Mars. The whir of its electric motors is a gentle hum in the thin Martian air. The crunch and grind of its 6 metal wheels on the alien soil is a rhythmic, percussive beat. Through its cameras, we see a panoramic vista that is hauntingly familiar, yet deeply strange. We see the clear outlines of an ancient river delta, the unmistakable fan-shaped deposit of sediment where a great river once flowed into a vast lake, billions of years ago. The rocks are a deep, ruddy ochre, coloured by the iron oxide, the rust that permeates the Martian soil. The sky is not blue, but a pale pinkish tan, a result of the fine red dust suspended in its thin carbon dioxide atmosphere. Now, let us shift our senses to another world, our other neighbour, Venus. We have never heard its sounds or seen its surface with such clarity, because no machine can survive there for long. But through the data sent back by the heroic Soviet Venera probes in the 1970s and 80s, we can imagine the scene. It is a true vision of hell. The lander is crushed by an atmospheric pressure 92 times greater than Earth's, the equivalent of being 1 kilometre deep in our ocean. The temperature is a staggering 462 degrees Celsius, hot enough to melt lead. The sky is a perpetual oppressive canopy of sickly yellow, a thick haze of sulfuric acid clouds that forever hides the sun. It is a world baked, crushed, and corroded, a stark and terrifying contrast to the cold, silent desert of Mars. Exploring these worlds, even with robots, is an immense challenge. Landing on Mars, for example, is a famously difficult endeavour, an ordeal that NASA engineers have dubbed the 7 minutes of terror. A spacecraft arriving from Earth is travelling at about 20,000 kilometers per hour. It has to slow down to a complete stop on the surface in just 7 minutes. The problem is Mars's atmosphere. It's thick enough to generate incredible heat from friction, requiring a massive heat shield to prevent the probe from burning up. But it's far too thin, less than 1%, the density of Earth's, to slow the craft down sufficiently with just a parachute. After the parachute has done all it can, the lander is still plummeting towards the ground at hundreds of kilometers per hour. This is where modern missions have employed a breathtakingly complex system called the sky crane. The lander detaches from the parachute and fires powerful retro rockets to slow its final descent. Then, a few meters above the surface, the rocket-powered crane lowers the rover down on a set of cables. The moment the rover's wheels touch the ground, the cables are cut, and the sky crane flies away to crash at a safe distance. This entire, perfectly choreographed sequence must be completed autonomously by the spacecraft's computer, as the radio signal from Mars takes about 11 minutes to reach Earth, meaning, by the time we on the ground receive the signal that the process has begun, the rover is already either safely on the surface or is a crater of wreckage. The two worlds our robots have explored tell two very different stories about the life of a planet. Venus is a cautionary tale. It is often called Earth's twin because it is similar in size and composition. It likely once had liquid water oceans, much like the early Earth. But its proximity to the Sun triggered a runaway greenhouse effect. As the planet warmed, its oceans began to evaporate. Water vapor is a powerful greenhouse gas, so this trapped even more heat, which caused the oceans to evaporate even faster. This vicious cycle was amplified as carbon dioxide, baked out of the planet's rocks, filled the atmosphere. The end result is the infernal world we see today, a powerful and terrifying reminder of how fragile a planet's climate can be. Mars, on the other hand, tells a story of loss. The evidence of ancient rivers, lakes, and perhaps even oceans is now overwhelming. It was once a warmer, wetter world, a place that might have been hospitable to life. But it lost its global magnetic field early in its history, and without that protective shield, the sun's solar wind slowly but surely stripped away its atmosphere, turning the planet into the cold, dry desert it is today. Our search for life reflects these histories. On Mars, we are archaeologists. The Perseverance rover is drilling rock cores and caching them in sealed tubes on the surface. The plan is for a future mission to retrieve these samples and return them to Earth, where our most powerful laboratories can search them for biosignatures, the chemical and fossilized traces of ancient microbial life. On Venus, the search is more speculative. While the surface is inhospitable, some scientists have theorized that microbial life could potentially survive floating high in the cooler, upper layers of the Venusian clouds. These robots are our senses, extended across the vast emptiness of space. They are our eyes, our ears, our hands, our tireless proxies in worlds too hostile for us to yet visit in person. They are lonely pioneers, working diligently in the silence and the dust, dutifully sending back postcards from the edge of what we thought was possible. Through their data, we have walked the rusty plains of Mars and peered through the acid clouds of Venus. They have shown us that our solar system is not just a collection of sterile rocks, but a family of worlds with rich, complex, and dramatic histories, each one a universe of discovery in its own right. Our robots have explored the rocky inner sanctum of our solar system, but beyond the orbit of Mars, beyond the asteroid belt, lie the true giants. What happens when we venture into the outer realm, the kingdom of gas and ice? Imagine a storm. Not a storm of wind and rain, but a swirling, crimson vortex of clouds, so vast it could swallow our entire planet whole, with room to spare. Imagine this storm has been raging, uninterrupted, for at least 400 years, a permanent, angry eye on the face of a world 1,000 times the volume of our own. This is the great red spot of Jupiter, and it is our first glimpse into the sheer, mind-bending scale of the outer solar system. To travel here is to leave the familiar realm of solid ground and enter a kingdom of giants. Worlds made not of rock and soil, but of gas and liquid, and pressures so immense they defy our everyday intuition. These are not just planets, they are titans, and they move to the rhythm of a slow, majestic, cosmic ballet. Let us fly now, in our imaginations, alongside the Juno spacecraft, a solar-powered explorer in orbit around Jupiter. Its path is a daring, looping dive that takes it from the far reaches of the Jovian system to just a few thousand kilometers above the planet's swirling cloud tops. As we plunge towards the planet, we witness sights of incredible beauty and violence. We fly through auroras, curtains of shimmering light larger than the entire Earth, sparked by the planet's colossal magnetic field. Then we are over the clouds, and they are not the gentle, puffy whites we are used to. They are an artist's canvas, a turbulent masterpiece of swirling whites, deep oranges, rich browns, and subtle blues. They are organized into distinct bands and zones, flowing in opposite directions at hundreds of kilometers per hour. And within these bands are storms, vortices, and cyclones, some small, some gargantuan, creating intricate patterns that look more like a Van Gogh painting than a weather system. Now, let us leave this turbulent world and drift outwards to its elegant neighbour, Saturn. We join the late, great Cassini probe on its long, peaceful vigil. From a distance, Saturn's rings appear as solid, ethereal bands of pale gold, a perfect, celestial halo. But as Cassini draws closer, and as it performs its final, daring dives through the gap between the planet and its rings, we see their true nature. They are not solid at all. They are a blizzard, a vast, shimmering river of countless individual particles of water ice, each in its own perfect orbit around the planet. The particles range in size from tiny dust grains to chunks as large as a house. And the rings themselves, which stretch for hundreds of thousands of kilometers, are in most places astonishingly thin, perhaps no more than 10 meters from top to bottom. We are flying alongside a structure as wide as a continent, yet as thin as a two-story building. Reaching these giant worlds was one of the greatest triumphs of our robotic exploration, and it was made possible by a remarkably clever trick of celestial mechanics. The gravity assist, or the slingshot maneuver. The Voyager probes, which performed the legendary grand tour of the outer solar system in the 1970s and 80s, did not have powerful enough rockets to get them all the way to Uranus and Neptune on their own. Instead, they used the planets themselves as cosmic accelerators. As Voyager approached Jupiter, for instance, it fell into the planet's immense gravity well. Jupiter's gravity pulled the spacecraft in, dramatically increasing its speed. The probe then swung around the back of the planet and was flung back out into the solar system. In this exchange, the tiny spacecraft stole an infinitesimally small amount of Jupiter's vast orbital energy, translating it into a massive boost in its own speed. By carefully choreographing these encounters with Jupiter, Saturn, and Uranus, mission planners sent the Voyager probes hurtling through the solar system at speeds far greater than any rocket could have provided, a perfect example of using the universe's own rules to our advantage. These worlds are called gas giants, but that name is a little misleading. They are not simply big, uniform balls of gas. Deep within Jupiter and Saturn, the pressures are millions of times greater than on Earth's surface. Under this immense, crushing force, the most common element in the universe, hydrogen, is thought to undergo a remarkable transformation. It ceases to be a gas and is compressed so tightly that its electrons are squeezed free from its atoms, and it begins to behave like a metal. This liquid metallic hydrogen is an excellent conductor of electricity. The rapid rotation of these planets, combined with the convection currents in this vast metallic ocean, generates the most powerful magnetic fields in the solar system, forces that trap radiation and create those spectacular auroras. Saturn's rings, too, are more than just a beautiful spectacle. They are a dynamic, evolving system, a laboratory for understanding how solar systems form. Their origin is still a mystery. Perhaps they are the shattered remains of a moon or a comet that strayed too close to the planet and was torn apart by its powerful gravity. Or perhaps they are leftover material from the formation of Saturn itself, pristine remnants from 4.5 billion years ago. Tiny shepherd moons orbit within and alongside the rings, their gravity sculpting the ice particles into sharp edges and intricate, braided patterns. In these distant realms, we see that a planet can be more than just a single world. These giants are the centers of their own complex systems, with dozens of moons, intricate rings, and powerful magnetic forces shaping their environments. They are like miniature solar systems, each with its own family of diverse and fascinating objects. Their sheer scale and alien nature serve as a profound reminder that our own Earth, with its solid ground, its gentle weather, and its thin, breathable atmosphere, is a delicate and precious exception in the cosmic rulebook. And the moons that orbit these giants are not just barren rocks. They are worlds in their own right, holding secrets that might just change our understanding of life itself. One moon in particular, a small icy world orbiting Jupiter, holds the tantalizing and beautiful promise of a vast, hidden ocean. Can you picture an ocean? Not an ocean of sparkling blue under a warm yellow sun, but an ocean of perfect, eternal blackness. An ocean deeper and larger than all of Earth's oceans combined. An ocean that has never once, in 4.5 billion years, been touched by the light of its star. Imagine this colossal body of water locked away, hidden from the universe beneath a solid shell of ice, kilometers thick. This is not a flight of fancy. This is the world that scientists believe exists on Europa, the fourth largest moon of Jupiter. It is a world that has, in the last few decades, become perhaps the most tantalizing and hopeful place in our solar system to ask the profound question: are we alone? It is a promise, sealed in ice, waiting for us in the cold and distant realm of the giants. Let us now embark on a speculative journey. We leave the harsh, radiation-filled space around Jupiter and descend towards Europa's bright, icy surface. From a distance, it looks like a cracked eggshell or a white porcelain ball, crisscrossed with a web of long, reddish-brown lines and fractures. This is a young and active surface. The lack of craters tells us it is constantly being repaved and renewed from below. We choose a spot and we dive, plunging down through the solid, frozen crust. For the first kilometer, the ice is brittle and cold, about -160 degrees Celsius. But as we go deeper, the immense pressure from the ice above and the faint warmth from the world below begins to change its consistency. The ice becomes warmer, softer, more like the ice at the bottom of a terrestrial glacier. We continue down through 10, maybe 20 kilometers of solid ice. And then, something changes. The ice gives way, and we are floating in liquid. We have arrived. We are in the hidden ocean of Europa. The darkness here is absolute, a pressure of blackness that the human mind can barely comprehend. The silence is profound, broken only by the distant, groaning sounds of the immense ice shell, shifting and cracking high above us, a sound that echoes for miles through the water. We are in an alien sea, on a world 500 million miles from home. We turn on our lights, and their beams cut through the darkness, revealing nothing, just an endless expanse of water. But we journey downwards, towards the seafloor, another 100 kilometers below us. And as we approach the rocky core of this moon, we might see it, a plume of black, superheated water gushing from a crack in the rock, a hydrothermal vent. Here, on the floor of this sunless sea, is a source of chemical energy and vital minerals, an oasis of warmth in the eternal night. And clustered around this vent, in this impossible place, we might, just might, find life. This incredible vision of a subsurface ocean is not just wishful thinking. It is built on decades of compelling scientific evidence. Our first major clues came from NASA's Galileo probe, which studied Jupiter and its moons in the 1990s. As it flew past Europa, its magnetometer detected a peculiar disturbance. The moon's magnetic field was behaving exactly as you would expect if it contained a large, hidden layer of something that conducts electricity, like a vast ocean of salty water. More recently, the Hubble Space Telescope has provided even more dramatic evidence. On several occasions, it has observed what appear to be enormous plumes of water vapor erupting from the moon's surface, shooting hundreds of kilometers out into space. It seems that cracks and fissures in the ice shell occasionally open up, allowing the ocean from below to spray out into the vacuum, a temporary geyser on a frozen world. But if this ocean exists, how does it stay liquid so far from the sun, in a place where temperatures on the surface are cold enough to freeze nitrogen solid? The answer is a beautiful cosmic dance of gravity. Europa is locked in a gravitational tug-of-war. The immense pull of Jupiter tries to keep it in a perfect orbit, but the gravitational nudges from the other large moons, Io and Ganymede, pull it slightly away. The result is that Europa's orbit is not a perfect circle, but a slight ellipse. This means its distance to Jupiter is constantly changing, and as it gets closer and further away, the planet's colossal gravity stretches and squeezes the little moon. This constant flexing, this kneading of the entire world, creates a tremendous amount of friction deep within its rocky core, generating heat. This process, called tidal heating, provides enough steady, internal energy to keep a vast global ocean from freezing solid beneath its insulating blanket of ice. This brings us to one of the most exciting possibilities in all of science. On Earth, in the 1970s, when we first explored the deep ocean floor, we found something miraculous. Around hydrothermal vents, where hot, mineral-rich water billows out from the planet's interior, we found entire ecosystems teeming with strange and wonderful life, from giant tube worms to pale, ghostly fish. These ecosystems thrive in total darkness and under crushing pressure. Their source of energy is not the sun. They do not rely on photosynthesis. Instead, they rely on chemosynthesis, a process where organisms derive their energy from chemical reactions, using the sulfur compounds that gush from the vents. These deep-sea vents on Earth provide a perfect and powerful analogue, a proof of concept for how life could exist on Europa. The necessary ingredients are all there. We have strong evidence for liquid water. The tidal heating provides a source of energy, and the interaction between the water and the rocky seafloor would provide the necessary chemical nutrients. Life might not need the light of a sun at all. It may only need a gentle, persistent warmth and the right chemical brew. Europa has forced us to fundamentally rethink what we mean by a habitable world. The search for extraterrestrial life has so often been a search for another Earth, a planet orbiting its star at just the right distance for liquid water to exist on its surface. But Europa teaches us that the conditions for life might be far more varied, and that some of the most promising worlds in the galaxy might be hidden, silent, icy moons orbiting far from the gentle warmth of their parent stars. We have journeyed from our home, past the rocky worlds, past the gas giants, to the hidden oceans of their moons. We have reached the very edge of the sun's planetary kingdom. But what marks the true boundary of our solar system? Where does the sun's influence finally end, and the great galactic ocean truly begin? Imagine the wind. Not the wind that rustles the leaves in the trees or cools your skin on a summer day, but a wind on a scale that is almost beyond comprehension. This is the solar wind, a constant, supersonic stream of charged particles, a plasma that blows outwards from the sun in all directions. It is the sun's breath, and it travels for billions upon billions of kilometers, far beyond the orbit of the most distant planet. For the entire journey we have taken so far, from Earth to Europa, we have been deep inside this solar wind. But what happens when this wind, after traveling for so long, finally runs out of steam? What happens when it collides with the even more tenuous wind that blows between the stars? Imagine it hitting a wall. Not a solid wall, but an invisible, magnetic boundary. A place of cosmic turbulence where the sun's breath finally yields to the vast, interstellar gales of the Milky Way galaxy. This boundary has a name. It is the heliopause, and it is the true edge of our solar system. Let us travel now on the last leg of our outward journey, riding alongside the most distant object ever made by human hands, the Voyager 1 spacecraft. For decades, since its launch in 1977, this tireless probe has been flying through the familiar environment of the heliosphere, the giant magnetic bubble inflated by the solar wind. Its instruments have been constantly tasting the particles around it, and for 35 years, the story was much the same. A steady stream of low-energy particles originating from our own sun. But in the summer of the year 2012, as Voyager 1 reached a distance of some 18 billion kilometers from home, its instruments began to detect a profound change. The familiar solar particles, the ones that had been its constant companions for its entire journey, suddenly and dramatically dropped off, their numbers dwindling to almost nothing. At the exact same time, the spacecraft was hit by a surge of new particles, of a completely different character. These were galactic cosmic rays, high-energy atomic nuclei that had been forged in the hearts of distant, ancient supernovae, and had travelled across the galaxy for millions of years. For its entire life, Voyager had been shielded from the full force of these rays by the heliosphere. Now, that shield was gone. The magnetic field around the probe also shifted, changing its orientation. The message from the data was clear and unambiguous. After a 35-year journey, Voyager 1 had crossed over. It had left the solar system. To understand this momentous crossing, we need to picture this bubble, the heliosphere. The solar wind blows outwards, creating a bubble of solar influence in the interstellar medium, which is the sparse mixture of gas, dust, and cosmic rays that fills the space between the stars in our galaxy. The heliosphere is like a ship, and our solar system is its crew, sailing through the galactic ocean of the interstellar medium. The heliopause, then, is the bow wave of this ship. It is the boundary where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar medium. It's the point where the two winds meet in a great, invisible standoff. The size and shape of this bubble are not static. It breathes and ripples as the sun's activity changes and as it moves through different regions of the galaxy. When Voyager 1 crossed this boundary in August of 2012, it was at a distance of about 122 astronomical units. That is 122 times the distance from the Earth to the Sun. Light from the Sun takes more than 17 hours to travel that far. Its sister ship, Voyager 2, which travelled in a different direction, crossed the heliopause in 2018 at a distance of about 119 astronomical units, confirming that our solar bubble is not a perfect sphere, but is likely squashed and distorted by its journey through the galaxy. So what is it like out there, in interstellar space? The word space suggests emptiness, but that is not quite right. It is a profoundly different kind of space than the one we have known. The density of the plasma, the gas between the stars, is actually higher than it is inside the outer heliosphere. And more importantly, the radiation environment is far more intense. Without the protective magnetic shielding of the heliosphere, the Voyager probes are now being constantly bombarded by the full, unmitigated fury of galactic cosmic rays. These are the whispers and echoes of the most violent events in the galaxy: exploding stars, clashing neutron stars, and the regions around supermassive black holes. Our probes are now truly in the realm of the stars, a place governed not by the familiar physics of our Sun, but by the collective physics of the entire Milky Way. They are floating in a medium that has been enriched by countless generations of stars that lived and died long before our own Sun was even born. For the entirety of human history, for the entire 4.5 billion year existence of our planet, we have lived our lives deep inside this protective solar bubble. Every myth we have ever told, every empire that has ever risen and fallen, every act of discovery and creation has taken place within the confines of the heliosphere. Now, two small, remarkable machines, built by human hands in the 1970s, have left that bubble. They are the first and only emissaries of humanity to ever enter interstellar space. They are profoundly, unimaginably far from home, so far that their faint radio signals, travelling at the speed of light, now take nearly a full day to reach us. They are our silent messengers, drifting ever outwards in the great galactic ocean, forever severed from the breath of the star that gave them, and us, life. They have left the solar system, but on the scale of the galaxy, their journey has only just begun. How far have they really gone? And as they drift on through the eons, what message do they carry from their tiny, distant world? If you had to create a single object, a single testament to all of human existence, to be sent out into the void and perhaps found by a stranger a billion years from now, what would you put on it? What images, what sounds, what ideas would you choose to represent the entirety of our complex, beautiful, and often tragic story? This was not a hypothetical question for the team led by Carl Sagan as they prepared the Voyager probes for their grand journey. Bolted to the side of each of these interstellar messengers is a golden phonograph record, a time capsule of our world, a greeting card to the cosmos. It is humanity's most ambitious attempt at a message in a bottle thrown into the cosmic ocean, and its contents are a poignant and hopeful portrait of a fragile, intelligent species, reaching out from their tiny, watery world. Let us listen, in our minds, to the sounds etched into the grooves of this golden record. It begins with greetings, 55 of them, in languages ancient and modern. It starts with Akkadian, a language spoken in Sumer over 6,000 years ago, and travels through the millennia, through Greek and Latin, Mandarin and Hindi, Welsh and Zulu, ending with the modern Chinese dialect of Wu. It is a chorus of humanity across time and space. Then come the sounds of our planet. The lonely call of a whale, the chirping of crickets, the rumble of a volcano, the gentle patter of rain, the roar of a train. There is the sound of a chimpanzee, the bark of a dog, and the sound of a human heartbeat, a rhythmic, universal pulse. There is the sound of a mother's first words to her newborn baby, and the sound of a kiss. And then there is the music. The record contains 90 minutes of the world's greatest music, a selection of breathtaking diversity. The mathematical perfection of Bach's Brandenburg Concerto, the defiant joy of Beethoven's Fifth Symphony, the soulful cry of Louis Armstrong's trumpet, the rebellious energy of Chuck Berry's Johnny B. Good. There are ancient percussion chants from Senegal, panpipe music from Peru, and the haunting, ethereal songs of the Navajo people. It is a mixtape for the Milky Way, a testament to our universal language of emotion and harmony. But this gift for the ears and the heart is also a gift for the mind. The record also contains 115 images, encoded in a simple, analog video format. They depict scenes of life on Earth, our science, and our civilization. There is a diagram of our solar system, a picture of the planets, a diagram of a human man and woman. There is an image of our DNA, the blueprint of our biology. There are pictures of forests and deserts, of insects and birds, of fish swimming in the sea. There is a picture of a woman tasting a grape, an X-ray of a human hand, and a group of children of all races looking up with curiosity. It is a visual encyclopedia of what it means to be alive on our world. Of course, all of this information would be useless if its finder could not understand it. And so, the cover of the record is itself a set of instructions, a beautiful and ingenious diagram etched in gold. The centerpiece of this diagram is a map. It shows the position of our Sun relative to 14 pulsars, which are the rapidly spinning, super-dense cores of dead stars. Pulsars flash with a precise, regular rhythm, like cosmic lighthouses. Their unique frequencies are listed on the map in binary code. Because pulsars slow down at a known rate, this map serves as both a galactic address and a cosmic clock. Any advanced civilization could use it to pinpoint where the message came from in the galaxy, and when it was sent. The cover also includes a diagram of the two lowest states of a hydrogen atom, the most common element in the entire universe. The transition between these two states provides a fundamental and universal unit of time, which can then be used to decode all the other information on the record. The Voyager Golden Record is a masterpiece of hopeful ingenuity, but its creators were also realists. The chances of it ever being found by an extraterrestrial intelligence are infinitesimally small. The probes are not aimed at any particular star, they are simply drifting through the void. They will not come close to another star system for at least 40,000 years. So why do it? The philosophy behind the record, as Sagan and his colleagues often expressed, was that this project was as much for us as it was for any potential aliens. The act of creating the record forced us to think about who we are. It forced us to confront the challenge of summarizing our entire existence, of choosing the best of ourselves to send out into the dark. It was a symbolic gesture, a statement that even if we are alone, we existed, we dreamed, we created beauty, and we tried to reach out. The record is a testament to the hope that lies at the heart of the scientific endeavor. Long after our sun swells into a red giant and engulfs our planet, long after all trace of human civilization has been erased, these two tiny golden artifacts will continue their silent journey. They will likely outlast the Earth itself, carrying the ghost of our music and our mathematics, the echo of our laughter and our curiosity, through the starry expanse for billions of years to come. The golden record travels on a physical object, a tangible piece of us. But most of our messages to the cosmos have been far less deliberate and far more chaotic. How far have our invisible whispers, our accidental shouts, our radio waves, traveled into the great silence? Imagine the scene. It is the 1st of August, 1936, in Berlin, Germany. The opening ceremony of the Olympic Games is underway. Powerful radio transmitters are broadcasting the sounds of the ceremony, the speeches, the music, the roar of the crowd out to the world. For those who listened, the signal was a fleeting, momentary experience. But that broadcast did not simply stop at the edge of the atmosphere. It continued traveling outwards, away from the Earth, at the fastest speed the universe allows. The speed of light. That very radio signal, the ghostly echo of a summer's day almost a century ago, is still traveling. Right now, it is washing over stars and any potential planets that lie some 90 light-years away from us. It is an accidental message, an unintentional whisper from our past, continuing its journey into the vastness of the galaxy. This single broadcast is just one of countless threads in a vast, invisible structure that we have been weaving around our planet for the last century. Let us now pull back from the Earth and try to visualize this structure. Picture a bubble, a perfect sphere, with our planet at its absolute center. The surface of this bubble is expanding outwards in every direction at the speed of light. This is our radiosphere. Its edge represents the furthest point that the very first, powerful, deliberate radio signals from human civilization have reached. And everything inside that bubble, a sphere of space now nearly 200 light-years in diameter, is filled with the faint, overlapping, and chaotic echoes of our modern age. It is a sphere filled with our noise. Inside this sphere are the radio ghosts of history. The declaration of the Second World War, the first rock and roll songs, the broadcasts of the Apollo moon landing, every television show, every commercial, every military communication, every stray signal from a mobile phone. It is a cacophonous, unintentional autobiography of our species, a messy and unfiltered collage of our triumphs, our follies, our art, and our conflicts, all radiating outwards into the cosmos. Any technological civilization living on a planet that is currently inside this sphere could, in principle, detect us. They could be listening to our history, with a time delay corresponding to their distance from us. A civilization 50 light-years away could be receiving the television broadcasts of the 1970s. But the chance of this is incredibly slim, due to a fundamental law of physics. The inverse square law. Think of the energy of a radio signal as a finite amount of paint. When the signal is broadcast from Earth, that paint is concentrated on a small sphere. As the sphere expands, that same amount of paint has to cover a vastly larger surface area. The signal's strength, its brightness, diminishes with the square of the distance it travels. By the time a television broadcast from Earth reaches even the nearest star, Proxima Centauri, which is just over 4 light-years away, its signal is so fantastically weak that it has become utterly indistinguishable from the natural, random radio noise generated by stars, gas clouds, and the background radiation of the universe itself. Our accidental message is almost certainly too faint to be understood, a whisper lost in a cosmic hurricane. Recognizing this limitation, we have on occasion tried to shout into the darkness with purpose. The most famous attempt was the Arecibo message, broadcast in 1974 from the Arecibo radio telescope in Puerto Rico. This was not a diffuse, omnidirectional broadcast like a TV show. It was a powerful, narrowly focused beam of radio waves, aimed deliberately at a specific target. A globular cluster of stars known as Messier 13, or M13. The message itself was a simple, pictorial representation of us, designed by Frank Drake and Carl Sagan. Encoded in binary, it contained a diagram of our number system from 1 to 10, a list of the atomic numbers for the key elements of life: hydrogen, carbon, nitrogen, oxygen, and phosphorus, and the formulas for the sugars and bases in our DNA. It included a simple stick figure diagram of a human, our average height, the population of Earth at the time, a map of our solar system highlighting our planet, and a picture of the Arecibo telescope itself. It was a concise, elegant summary of our science and our biology. But M13 is 25,000 light-years away. The Arecibo message will take 25,000 years to arrive at its destination. And if any civilization there were to receive it, decode it, and send a reply, that reply would take another 25,000 years to travel back to us. It was a message sent with no expectation of an answer, an act of cosmic optimism on a geological timescale. So, we are left with this strange reality. We are surrounded by a sphere of our own making, an expanding bubble of our own voice. It is our unintentional mark on the galaxy, a sphere of influence that grows by 1 light-year every year. It is a messy, unfiltered, and probably unintelligible broadcast of who we are. This raises a profound and unsettling question. If someone, or something, is listening, what would they think of us, based on the chaotic signals that leak from our world? And perhaps an even more important question, should we be shouting into the cosmic darkness at all? Some have argued that broadcasting our existence is a reckless gamble, that we should listen quietly before we advertise our presence to a galaxy whose inhabitants might not be friendly. For now, the debate is academic. The whispers have already been sent, and they are travelling outwards, carrying the story of a noisy, young civilization with them. We have sent our voices and our machines out into the galaxy, but in doing so, we talk of distances in light years, numbers so vast they strain our imagination. How do we even know these distances? What kind of cosmic yardstick can we possibly use to measure the immense, silent void between the stars? How do you measure the distance to something you cannot possibly touch? Something so remote that its light has taken centuries, or even millennia, to cross the gulf of space and reach your eyes. This is one of the most fundamental challenges in all of astronomy, the bedrock upon which our entire understanding of the universe is built. We speak of our radio signals reaching stars dozens of light years away, but how do we know they are dozens of light years away? We cannot simply stretch out a cosmic measuring tape. The answer is one of the most beautiful and ingenious creations of the human intellect, the cosmic distance ladder. It is not a single method, but a series of clever, overlapping techniques, where each step, or rung, allows us to calibrate the next, letting us climb from our nearest stellar neighbours all the way out to the edge of the observable universe. To understand the first and most important rung of this ladder, let us begin with an experience you can have right here on Earth. Imagine you are an ancient astronomer, standing in a large open field. In the middle of the field stands a single, familiar tree. In the far, far distance, beyond the field, is a great, unmoving mountain range. Now, as you hold your gaze on the tree, you take a few steps to your left. From your new vantage point, you notice something. The tree appears to have shifted its position against the backdrop of the distant mountains. You walk a few steps to your right, and the tree seems to shift back again. This apparent shift in the position of a nearby object against a distant background, caused by a change in your viewing angle, is called parallax. Now, let us scale this up to the heavens. The tree is a nearby star. The distant mountain range is the backdrop of far more remote, seemingly fixed stars. And the distance you walk from left to right is the colossal diameter of the Earth's orbit around the Sun. As the Earth travels from one side of its orbit to the other over the course of 6 months, a nearby star will appear to wobble back and forth ever so slightly against the distant cosmic background. By measuring the tiny angle of this wobble and knowing the precise width of Earth's orbit, we can use simple trigonometry to calculate the star's distance. This is the gold standard of cosmic measurement, a direct, geometric calculation. But it only works for our closest neighbours, out to a few thousand light years. Beyond that, the angle of the shift becomes too small to measure accurately, and we must step up to the next rung on the ladder. This second rung relies on finding standard candles, objects whose true, intrinsic brightness we can somehow know with great certainty. Imagine you are in a dark field at night, and you see two lights. One is very bright, and one is very dim. You cannot know if the bright one is a powerful searchlight far away, or a faint candle held right in front of your face. But if you knew, somehow, that both lights were identical 100-watt light bulbs, you could instantly tell that the dimmer one was much further away. In the early 20th century, an astronomer at Harvard named Henrietta Leavitt discovered a cosmic standard candle. She was studying a class of pulsating stars called Cepheid variables. These stars rhythmically brighten and dim with a precise clockwork regularity. Leavitt's groundbreaking discovery was that there is a direct, unwavering relationship between the period of a Cepheid's pulsation and its true, intrinsic brightness. The longer it takes to pulse, the brighter the star actually is. This was a monumental breakthrough. Now, astronomers could look for these Cepheids in distant star clusters. They could measure the time it took for the star to pulse, which would tell them its true luminosity, its wattage. Then, by comparing that true brightness to how dim it appeared in their telescopes, they could calculate its distance. It was this very technique that allowed Edwin Hubble in the 1920s to measure the distance to the Great Nebula in Andromeda, proving it was not a gas cloud in our own galaxy, but a colossal, separate island universe, a galaxy in its own right, millions of light years away. But even Cepheids have their limits. They become too faint to see in the most remote galaxies. To reach the truly cosmic scales, we need a much brighter candle. We need a standard bomb. We find this in a specific type of stellar explosion known as a Type 1a supernova. These cataclysmic events occur in binary star systems, where a small, dense star called a white dwarf is orbiting a larger companion star. The white dwarf's powerful gravity pulls material from its companion, gradually accumulating more and more mass. It continues to feed until it reaches a very specific, critical limit, a mass of about 1.4 times that of our Sun, known as the Chandrasekhar limit. At this precise point, the pressure in the star's core becomes so immense that it triggers a runaway thermonuclear explosion. The entire star is consumed in a matter of seconds, in a blast of light so brilliant it can briefly outshine its entire host galaxy. Because every Type 1a supernova is triggered at the exact same mass, they all go off with almost the exact same peak brightness. This makes them the most perfect standard candles imaginable. When we spot one of these explosions in a galaxy billions of light years away, we know precisely how bright it truly is. And by measuring how dim it appears, we can calculate its distance with incredible confidence. It is by using these supernovae that we have mapped the large-scale structure of the universe and discovered that it is expanding at an accelerating rate. Our knowledge of the cosmos is not built on a single observation, but on this beautiful, self-correcting ladder, built step by step upon the foundations of geometry, the physics of pulsating stars, and the final, brilliant death throes of ancient suns. It is a monument to generations of human ingenuity. Using this ladder, we have meticulously mapped the stars in our immediate corner of the galaxy. So what does this cosmic map tell us? What does our neighborhood actually look like? Imagine that our Sun, with its family of planets, is not traveling through a typical bustling neighborhood of the Milky Way. Imagine instead that for millions of years we have been drifting through a vast, cavernous, and strangely empty void. A bubble of near-nothingness, carved out of the galaxy by some ancient, violent event. This is not science fiction. This is our home. We live inside a structure known as the local bubble. It is a peculiar and specific address, a ghost in the grand machine of the galaxy, and our journey through it has profoundly shaped the very sky we see above us every night. It is a reminder that our place in the universe is not static, but is part of a dynamic and ever-changing journey. To picture this bubble, it helps to think of the space between the stars, the interstellar medium, as a kind of patchy, uneven fog. In most regions of the galaxy, this fog is a thin but ever-present mist of cold hydrogen gas and microscopic dust particles. But the region our solar system currently finds itself in is very different. We are in a great clearing in this fog. For the last 5 to 10 million years, our Sun has been coasting through an enormous, peanut-shaped cavity where the gas is 1,000 times less dense than the galactic average. This cavity, the local bubble, is vast, stretching about 1,000 light-years across. And while the gas inside it is incredibly sparse, it is also scorchingly hot, superheated to about 1 million degrees Celsius. We are floating through a tenuous, invisible plasma, a vast bubble of hot, empty space. So, where did this colossal bubble come from? How was such a huge void carved out of the fabric of the galaxy? The leading theory is a dramatic one. Astronomers believe that between 10 and 20 million years ago, a cluster of young, massive stars that existed near the bubble's center reached the end of their lives. One by one, they exploded. In a chain reaction lasting several million years, a series of about 15 powerful supernovae went off, like a string of cosmic firecrackers. Each explosion sent a powerful shockwave racing outwards into the surrounding interstellar gas. These successive shockwaves acted like a giant, cosmic snowplow, sweeping up the gas and dust and pushing it outwards, compressing it into a dense, expanding shell. The interior, scoured clean by these blasts and filled with their superheated remnants, became the low-density, high-temperature bubble we live in today. We are, in a very real sense, living inside the ancient wreckage of dead stars. The shell of this bubble, the wall of swept-up gas and dust, is still expanding outwards at about 6 kilometers per second. Our residence inside this peculiar structure has two profound consequences for us as observers of the universe. The first is that it gives us a remarkably clear view of what lies beyond. Because the bubble is so empty, there is very little obscuring gas and dust between us and the distant cosmos. This is why our night sky is so dark and so clear. If we lived in a dense, dusty molecular cloud, the kind of place where new stars are born, our view would be shrouded in a thick cosmic smog, and the faint light of distant galaxies would be almost impossible to see. Our clear window on the universe is a direct consequence of the ancient cataclysms that created our bubble. The second consequence is even more poetic. The very act of the supernovae sweeping up the interstellar medium into a dense shell has created a fertile ground for new creation. When gas and dust are compressed in this way, gravity can more easily take hold, causing clumps to collapse in on themselves and ignite as new stars. Many of the beautiful, young, blue stars you can see in the night sky, particularly in constellations like Scorpius and Centaurus, are part of stellar associations that formed right on the surface of our local bubble. The Sun itself is not a part of this star-forming region. It is just an older, unrelated star that happens to be passing through. But we are close enough to witness the creative aftermath of the bubble's violent birth. The shell of the bubble is a place where the ashes of one generation of stars are providing the raw material for the next. We often think of our place in the universe as fixed, as if we are simply sitting still in a static diorama. But the local bubble reminds us that we are on a journey. We are passengers on a starship, our solar system, which is cruising through the complex and evolving landscape of the Milky Way. We are currently passing through this strange and empty cavern, a phase of our journey that has lasted for millions of years and will likely continue for several million more before we exit the bubble and plunge back into the denser fog of the interstellar medium. This journey through the ancient wreckage of supernovae has given us our clear view of the heavens and has surrounded us with the beautiful nurseries of newborn stars. Our Sun is just one anonymous star among the hundreds of billions that make up our home galaxy. We have explored our immediate, peculiar neighborhood. But what does the entire city of stars itself look like, when seen from the outside, looking in? What is the grand structure of our Milky Way? Look up into the sky on a clear, moonless night, far from the glare of city lights. If you are lucky, you will see it. A faint, ethereal, and shimmering band of light, a milky path of countless unresolved stars stretching across the heavens. For most of human history, we have looked at this band with wonder, giving it names like the River of Heaven or the Winter Street. We have seen it as a celestial river, a path for the gods, a beautiful decoration on the celestial sphere. But the truth is something far more profound. When you look at that faint, glowing band, you are not looking at something in the distance. You are looking into the very heart of your own home. You are on the inside, looking through the densest part of our own galaxy, the Milky Way. It is the collective light of billions of suns, too far away to be seen individually, their light blending together into a soft, celestial glow. It is the architecture of our home, revealed. Let us now pull back on a journey of pure imagination, leaving our solar system behind. We watch as our sun shrinks, becoming just another anonymous star in a sea of stars. We pull back further, past the edge of the local bubble, until we are floating high above the galactic plane. From this vantage point, the true form of our home is revealed. It is a majestic, swirling pinwheel of light, a breathtaking spiral 100,000 light-years across. We see the bright, glowing central bar, a dense, elongated cluster of old, yellow stars at its heart. From the ends of this bar, great spiral arms curve outwards, like the arms of a celestial hurricane. These arms are painted with the brilliant blue light of hot, young, newborn stars, and traced with the dark, intricate lanes of cosmic dust that obscure the light from behind. It is a dynamic, living city of stars, slowly, gracefully, turning in the silent darkness. Our solar system is a tiny, insignificant speck, nestled within a minor spur of one of these great arms, a feature known as the Orion Arm. We are in the suburbs of this great galactic city, about 27,000 light-years away from the dazzling, chaotic rush of the galactic center. We are just one of the 100 to 400 billion stars that call this galaxy home. This colossal, spinning structure poses a profound cosmic puzzle. As astronomers began to measure the speeds of stars within our galaxy, they found something deeply strange. According to our understanding of gravity, formulated by Newton and refined by Einstein, the stars on the outer edges of the galaxy should be moving much more slowly than the stars closer to the center, just as the outer planets in our solar system, like Neptune, orbit the Sun much more slowly than the inner planets, like Mercury. But that is not what we see. The stars in the outer arms of the Milky Way are orbiting far too quickly. They are moving at such a blistering pace that the gravity from all the visible matter in the galaxy, all the stars, gas, and dust we can see, is not nearly strong enough to hold on to them. They should, by all rights, fly off into the lonely darkness of intergalactic space. The fact that they do not, the fact that our galaxy and others like it hold together at all, points to a mysterious and unseen ingredient. This invisible glue is what we now call dark matter. It is a strange, ghostly substance that does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. We only know it is there by the powerful gravitational pull it exerts on the things we can see. The current thinking is that our entire galaxy is embedded in a vast, spherical halo of this dark matter, which outweighs all the normal matter by a factor of about 6 to 1. It makes up about 85% of all the matter in the universe, and yet we still have no idea what it actually is. It is the invisible scaffolding upon which our entire galactic city is built. And at the very center of this city, at the gravitational heart of our galaxy, lies a monster. It is a supermassive black hole, an object with a gravitational pull so immense that nothing, not even light, can escape it. This object, named Sagittarius A star, is a true behemoth. It has a mass of about 4 million times that of our Sun, all condensed into a region of space smaller than the orbit of Mercury. We cannot see it directly, of course. It is the definition of darkness. But we can see its effects with stunning clarity. Using powerful telescopes, we can watch the frantic, dizzying orbits of the stars that are closest to the galactic center. These stars whip around an unseen central point at incredible speeds, some moving at several thousand kilometers per second. By tracking these orbits and applying the laws of gravity, we can calculate the precise mass of the object they are circling, the monster that lurks in the dark. This black hole is the gravitational anchor of the entire Milky Way. It is the drain at the center of the cosmic sink, around which our Sun, and every other star in the galaxy, is slowly, patiently revolving. Every star you see in the night sky, every twinkling point of light, is a neighbor. They are fellow citizens of this vast, spiral metropolis. We are all bound together by the familiar pull of gravity, and by the unseen grip of dark matter, all of us on a shared 400 billion star journey around a monstrous, hidden heart. Our galaxy is a magnificent island of stars, a self-contained universe of breathtaking beauty. But it is not alone. What lies in the endless, black ocean between these islands of light? Imagine for a moment that our galaxy, our beautiful, sprawling Milky Way, has siblings. Imagine it is part of a small, intimate family, with one other large, majestic sibling, and dozens of smaller, younger ones, all bound together by the gentle, invisible ties of gravity. Imagine them all dancing together in a slow, celestial waltz that has been unfolding over billions of years, a dance that will, one day, culminate in a spectacular embrace. This is not a metaphor. This is the reality of our place on the next scale of cosmic structure. Our Milky Way is a leading member of a small cluster of galaxies known as the Local Group. It is our cosmic neighborhood, our galactic family, and it is the setting for the next chapter of our story, a chapter that is already being written in the silent language of gravity and motion. Let us now zoom out once more, pulling our perspective away from the face of the Milky Way until our entire home galaxy is just a bright, swirling disk in the darkness. As we do, other shapes begin to emerge from the void. The first and most spectacular is another galaxy, a beautiful spiral very much like our own, but slightly larger. This is the Andromeda Galaxy, also known as Messier 31. It is our closest major galactic neighbour, and on a clear night, you can just barely see it with the naked eye as a faint, fuzzy smudge of light in the constellation Andromeda. It is the most distant object the human eye can see without aid, and dotted all around these two galactic titans, like moths circling a pair of great cosmic flames, are dozens of much smaller, fainter galaxies. These are the dwarf galaxies, small, irregular collections of a few billion stars, many of which are in orbit around their larger hosts. The two most famous of these are visible from the southern hemisphere: the Large and Small Magellanic Clouds, satellite galaxies that are slowly being torn apart by the Milky Way's gravity. Altogether, this collection of over 50 galaxies, all gravitationally bound and moving together through space, makes up our local group, a structure that spans a vast, 10 million light-year stretch of the universe. Within this galactic family, there is a great drama unfolding. For nearly a century, astronomers have been measuring the light from the Andromeda Galaxy, and they noticed something peculiar. The light from nearly every other galaxy we see is redshifted, meaning its wavelengths have been stretched out by the expansion of the universe, a sign that they are all moving away from us. But the light from Andromeda is blue-shifted. Its wavelengths are compressed. It is not moving away. It is coming right for us. By carefully tracking the motion of its stars, we have confirmed that the Milky Way and Andromeda are on a direct, unavoidable collision course. Hurtling towards each other at a speed of about 110 kilometers per second, these two majestic spirals are destined to merge. This colossal event is predicted to begin in about 4.5 billion years, roughly the same time that our Sun will be nearing the end of its life. The future galaxy that will result from this merger has already been nicknamed Milkomeda. So, what will this cosmic collision be like? The word collision conjures images of a violent, destructive crash, but that is not what will happen at all. The distances between individual stars are so mind-bogglingly vast that when these two galaxies merge, the number of actual, direct star-on-star collisions will be practically zero. Our Sun will not crash into another star. Instead, it will be a slow, majestic, and transformative gravitational encounter. Over the course of hundreds of millions of years, the two galaxies will pass through each other like ghosts. Their powerful, combined gravity will warp and distort their beautiful spiral structures, pulling out long, brilliant streamers of stars and gas in a phenomenon known as tidal disruption. The two galaxies will swing past each other, move apart, and then be pulled back together again by their mutual gravity, repeating this cosmic dance several times. During this process, the vast clouds of gas and dust in both galaxies will be compressed and squeezed, triggering a spectacular, galaxy-wide burst of new star formation. The night sky of any planet that survives this era will be a breathtaking sight, filled with the brilliant blue light of millions of newborn stars. Eventually, after perhaps 1 billion years of this gravitational tango, the two galaxies will settle down and merge completely. Their spiral arms will be gone, their stars will be randomized into new orbits, and a single, giant, elliptical galaxy will remain, larger and more massive than either of its parents. Our Sun and its planets will almost certainly survive the merger, but they will be thrown into a new, much larger orbit in a new and unfamiliar galaxy. This grand, inevitable merger reminds us that the universe is not a static, unchanging place. It is a dynamic and evolving entity, a place of constant creation, interaction, and transformation, even on the most massive of scales. The night sky we know and love is just a temporary snapshot in cosmic time. Our distant descendants, should they exist, may look up at a sky entirely alien to our own, a sky filled with the brilliant light of the great merger, the beautiful result of this long and graceful cosmic dance. Our local group, this small family of galaxies, is just one small cluster in the cosmos. But is it an island, floating alone? Or is it part of an even grander structure? As we pull back even further, what patterns do we see? How is the universe organized on the very largest of scales? If you could zoom out from our local group, so far that entire galaxies, even majestic spirals like the Milky Way and Andromeda, were just tiny, insignificant points of light, what pattern would they make? Would the universe on its grandest scale be a random, uniform scattering of these galactic specks, like dust sprinkled evenly across a vast, dark floor? Or would some hidden order, some grand architecture, begin to reveal itself? For most of human history, we assumed the universe was largely homogeneous, the same in every direction. But in the last few decades, as our telescopes have peered deeper and our maps have grown larger, we have discovered the breathtaking and unexpected truth. The universe is not random. It is not a uniform soup of galaxies. On the largest of scales, it is held together by a vast, intricate, and beautiful structure. The cosmic web. Imagine floating in a space so vast that you can hold the entire observable universe in your view. What you see is a stunning, three-dimensional network of unimaginable size and complexity. It looks almost organic, like the interconnected neurons of a colossal brain, or the delicate, luminous strands of a spider's web stretching across the cosmos. This web is made of galaxies. They are not scattered randomly, but are arranged in long, thin, glowing filaments, great rivers of galaxies that snake through the void for hundreds of millions of light years. Where these filaments cross and intersect, the galaxies are clustered together in dense, bustling knots. These nodes are the great superclusters, the major metropolitan hubs of the universe. And connecting these filaments are vast, flattened sheets of galaxies, known as galactic walls. But the most striking feature of this cosmic map is not the structures themselves, but the spaces in between them. The majority of the universe's volume is taken up by the great cosmic voids. These are colossal, almost perfectly empty regions of space, some of them hundreds of millions of light years across, containing very few, if any, galaxies. They are the great, silent deserts of the cosmos. Our own small local group is just a tiny, anonymous resident of this web. We are located on the outskirts of a larger structure called the Virgo supercluster, which itself is just one tendril of an even more gargantuan supercluster that astronomers have named Laniakea, a Hawaiian word meaning immeasurable heaven. We live on a filament, on the edge of a great cosmic void. The origin of this magnificent, web-like structure is one of the most beautiful stories in all of science. A story that connects the largest things we can see with the smallest things we can imagine. The story begins in the very first moments after the Big Bang. In that incredibly hot, dense, primordial state, the universe was not perfectly smooth. There were tiny, microscopic, random fluctuations in the density of energy, governed by the strange laws of quantum mechanics. These were quantum jitters, impossibly small variations, 1 part in 100,000, from one place to another. As the universe expanded and cooled, these tiny seeds of structure were stretched to astronomical proportions. And then, gravity went to work. For billions of years, gravity has been patiently and relentlessly amplifying those initial, tiny differences. The regions that were, by pure chance, infinitesimally denser than their surroundings, began to exert a slightly stronger gravitational pull. They pulled in more and more matter, especially the invisible dark matter that acts as the universe's scaffolding. Over eons, this process created a runaway effect. The rich got richer as matter streamed along invisible highways from the less dense regions and collected in the denser ones. The denser regions became the filaments and the superclusters of the cosmic web. The less dense regions, having had all their matter drained away, were emptied out, becoming the great cosmic voids. The grand cosmic skeleton we see today is a direct, large-scale photograph of quantum uncertainty, frozen into the fabric of space-time from the first trillionth of a second of the universe's existence. And what of the matter itself? We now know that the stars and galaxies we see, the glowing parts of the filaments, are just the tip of the cosmic iceberg. Most of the normal matter in the universe, the stuff made of protons, neutrons, and electrons, is not actually locked away inside galaxies. It exists as an incredibly hot, thin, and almost invisible gas that fills the vast spaces between the galaxies, tracing the paths of the great filaments. This is the intergalactic medium. We can only detect it indirectly, by seeing how it absorbs the light from extremely distant objects called quasars. This gas is the great reservoir of the cosmos, the fuel tank from which galaxies draw in the material they need to form new generations of stars. The galaxies are just the bright, condensed points, the luminous foam on the deep, invisible ocean of matter that makes up the true substance of the cosmic web. The universe is not random at all. It possesses a profound, hidden, and breathtakingly organic structure. We live on a tiny planet, orbiting a single star in one galaxy, located on a glowing filament of a cosmic web that stretches for billions upon billions of light years. There is a deep and mysterious order to it all. We have reached the largest observable structures in the cosmos, but this entire, colossal web is expanding. What happens when we stop looking out in space and instead try to look back in time, all the way to the very beginning of it all? Imagine, if you can, that you could see the afterglow of creation itself, not with your eyes, not as a bright flash, but as a faint, ancient, and persistent light that fills all of space, coming from every direction at once. Imagine you could see a baby picture of the entire universe, a snapshot taken when it was just a newborn, long before the first stars or galaxies had ever formed. This is not a fantasy. This light is real. It is all around us, all the time. It is called the cosmic microwave background, and it is the oldest, most distant, and most profound thing we have ever observed. It is the echo of the Big Bang, a faint, warm whisper from the dawn of time. You have, in fact, almost certainly seen it yourself, without realizing it. If you have ever seen an old analog television, the kind with an antenna, and tuned it to a dead channel, you would see a screen full of flickering, black and white static, a visual snow. That static is caused by random radio waves being picked up by the antenna. Most of it is from local sources, from our own planet. But about 1% of that static, 1 in every 100 of those flickering dots, is interference from the cosmic microwave background. That television is acting as a crude radio telescope. You are, in that moment, literally seeing the echo of creation. Now, imagine a telescope, a sensitive radio observatory like the Planck satellite, that can see this light in exquisite detail. What it sees is not a uniform, featureless glow. It sees a mottled, dappled tapestry of light, an intricate map of tiny, almost imperceptible fluctuations in temperature. These fluctuations are the seeds of everything that exists today. It is the most important photograph ever taken. So what is this ancient light? And where did it come from? For the first 380,000 years after the Big Bang, the universe was an utterly alien place. It was incredibly hot, incredibly dense, and it was completely opaque. It was a roiling, primordial soup of fundamental particles, protons, neutrons, and electrons, and light particles, photons. In this infernal environment, the photons were constantly crashing into the free-floating electrons, being absorbed and re-emitted in a chaotic, cosmic pinball game. Light could not travel freely. The entire universe was shrouded in an impenetrable, glowing fog. But all the while, the universe was expanding, and as it expanded, it cooled. Eventually, it reached a critical temperature, about 3,000 degrees Kelvin. At this point, it was cool enough for the protons and electrons, which had been zipping around freely, to finally slow down and combine, forming the first stable, neutral hydrogen atoms. This moment is called recombination, and at that precise instant, the universe underwent a profound transformation. With all the free electrons now bound up inside atoms, the photons of light were suddenly free. The cosmic fog lifted. The universe, for the very first time, became transparent. The cosmic microwave background is that very first light, the light that was present everywhere in the universe at the moment of recombination, finally released to travel unimpeded through space. And for the last 13.8 billion years, it has been doing just that, streaming across the cosmos, growing fainter and cooler as the universe has continued to expand. The expansion of space itself has stretched the wavelengths of this ancient light, shifting it from the visible and infrared spectrum all the way down into the microwave part of the spectrum, which is where we detect it today. And what about those tiny, mottled fluctuations, those warmer and cooler spots on the map? These are the Rosetta Stone of cosmology. These tiny variations in the temperature of the light, on the order of just 1 part in 100,000, correspond directly to the tiny variations in the density of the primordial soup at the moment the light was released. The slightly hotter, redder spots on the map are the places where the matter was infinitesimally denser than average. The slightly cooler, bluer spots are where it was infinitesimally less dense. These were the seeds. These were the blueprints for the modern universe. Over the next 13.8 billion years, gravity took these minuscule density fluctuations and amplified them. The slightly denser regions pulled in more and more matter, eventually collapsing to form the first stars, the first galaxies, and the great superclusters of the cosmic web. The less dense regions were emptied out, becoming the vast cosmic voids. When we look at the cosmic microwave background, we are looking at the embryonic universe, seeing the genetic code that would ultimately give rise to every single structure we see in the cosmos today, including our own galaxy, our own sun, and our own planet. Its existence, its incredible uniformity across the entire sky, and the precise pattern of these tiny fluctuations were all stunning confirmations of the Big Bang Theory, and its discovery in 1965 is considered one of the most important scientific achievements of all time. No matter where we look in the sky, this ancient light is there. It is not coming from a particular place, it is coming from time itself. It is a fossil, an artifact of our cosmic birth. We are all, at this very moment, being bathed in the faint, gentle, and persistent afterglow of the beginning. This light marks the very edge of our visible universe, the furthest back in time we can possibly see. But is the edge of what we can see the same as the edge of the universe itself? What lies beyond this final, luminous horizon? We have arrived, in our journey, at the edge of everything we can see. The cosmic microwave background is a wall of light, a temporal horizon 13.8 billion years in our past. But this fact presents us with a strange and profound paradox, a riddle that seems to defy simple logic. If the universe is 13.8 billion years old, then the absolute furthest we can see is the distance light has been able to travel in 13.8 billion years. This seems to imply that the universe should be 13.8 billion light-years in radius, or about 27.6 billion light-years across. And yet, when astronomers do the calculations, they arrive at a much, much larger number. The current estimate for the diameter of the observable universe is a staggering 93 billion light-years. How can this be? How can a universe of a certain age be so much larger than the distance its own light could have travelled in that time? To unravel this beautiful cosmic puzzle, let us return to a simple, earthly analogy. Imagine you are standing on a great ship in the middle of a vast, calm ocean. You can see out to the horizon in every direction. That horizon is the edge of your own, personal, observable world. It is a perfect circle, a boundary defined by the curvature of the earth and the limitations of your sight. You know, with certainty, that the world does not end at your horizon. There is more ocean, more land, more world beyond it. You just cannot see it from where you are. The observable universe is very much like this, but with a crucial difference. Our horizon is not a horizon in space, but a horizon in time. Because the speed of light is finite, when we look out into the cosmos, we are also looking back into the past. We see the Andromeda galaxy, not as it is today, but as it was 2.5 million years ago. We see the light from the cosmic microwave background, not as it is today, but as it was 13.8 billion years ago. At the moment it was released. We are at the center of a great, spherical bubble of observation, and its edge is defined by the age of the universe. The edge of our observable universe is the point from which light has had just enough time in the entire history of the cosmos to travel from there to here. So, why is this bubble so much larger than expected? The answer lies in the single most important and counterintuitive fact about our universe. Space itself is expanding. When that ancient photon of light from the cosmic microwave background began its long journey towards us 13.8 billion years ago, the universe was a much smaller, denser place. But during the entire time that photon was traveling, the very fabric of space it was traveling through was stretching and expanding. Think of it like a tiny, determined ant walking along the surface of a balloon that is being steadily inflated. The ant is walking at its top speed, but the rubber surface it is walking on is constantly stretching out beneath its feet. By the time the ant has walked for 1 minute, the distance from its starting point will be much greater than the distance it was capable of walking in that minute. The same is true for that ancient light. The point in space that emitted that light 13.8 billion years ago was much closer to us when the journey began. But during that 13.8 billion year trip, the expansion of space has carried that point, that location, much, much further away from us. Today, astronomers calculate that the source of the most distant light we can see is now about 46.5 billion light-years away. Since this is true in every direction we look, the observable universe is a sphere with a diameter of about 93 billion light-years. This expansion of space itself does not violate Einstein's universal speed limit, which states that nothing can travel through space faster than light. The galaxies are not rocketing through space away from us. They are more like raisins in a loaf of baking bread. The raisins are not moving through the dough, but the dough itself is expanding, carrying all the raisins away from each other. The galaxies are just along for the ride. And what lies beyond this cosmic horizon? What is outside our 93 billion light-year bubble of observation? The simple, humbling answer is that we have no way of knowing. The full, complete universe is almost certainly vastly larger than the tiny patch of it we can see. It might even be infinite. There are almost certainly countless other galaxies, other cosmic webs, other wonders out there, beyond our horizon. But their light has not had enough time in the history of the universe to reach us yet. And for the most distant of them, their light never will. The expansion of space is accelerating, and the regions of space beyond our horizon are receding from us faster than the speed of light itself. Like the world beyond the horizon of our ship at sea, we know something is there, but it lies forever beyond our direct grasp. We are profoundly and beautifully limited by the cosmic speed limit and the age of time itself. What wonders, what other forms of existence, what other stories might be playing out forever beyond our sight? We have journeyed from our planet to the very edge of what we can see, the frontier of the outward gaze. Now, let us turn that gaze around. Let us journey inward. How far have we really gone in understanding the very stuff we, and everything else, are made of? Imagine a world, not in the distant cosmos, but deep within the fabric of everything around you. A world where the fundamental rules of reality seem to dissolve into a bizarre and ghostly dance. Imagine a world where a particle can be in multiple places at the exact same time, where the simple act of looking at something fundamentally changes what it is, and where the concept of emptiness is a lie, a place that is actually a boiling, chaotic sea of potential. This is not a mystical realm or a philosopher's dream. This is the quantum realm. It is the foundation upon which our entire, solid, predictable universe is built. It is the ultimate inner frontier, and our journey to understand it has taken us into a reality far stranger than any alien world we could ever imagine. Let us shrink ourselves down, leaving the world of human scales behind. We move past the familiar landscape of our senses, past the intricate machinery of a living cell, past the elegant architecture of a molecule. We continue down to the scale of a single atom. And here, our classical intuition begins to fail us. We see the nucleus at the center, not as a simple solid ball of protons and neutrons, but as a frantic, energetic cluster of particles bound by forces of unimaginable strength. And surrounding this nucleus, we see the electrons. But they are not the tiny, planet-like specks we were taught about in school, dutifully orbiting the nucleus in neat, clean circles. Instead, they are something far more ethereal and strange. An electron in an atom exists as a cloud, a shimmering, hazy sphere of probability. It has no definite location. It is not a thing in a place. It is a smear of potential, existing in all of its possible locations around the nucleus at once. It is everywhere and nowhere simultaneously, a ghost in the atomic machine, until the moment we try to find it. This ghostly nature is one of the foundational principles of quantum mechanics, a concept known as superposition. A quantum particle, like an electron, can exist in a combination of multiple, mutually exclusive states, all at the same time. The famous thought experiment of Schrödinger's cat was designed to illustrate the sheer absurdity of this idea when applied to our everyday world. In the quantum realm, an electron can be both spin up and spin down at the same time. It is only when we make a measurement, when we interact with it, when we look at it, that this cloud of probability is forced to make a choice. The instant it is measured, its wave function collapses, and it settles into one single, definite state. The universe, it seems, only decides what it is when we ask it to. Before the measurement, there is only potential. After, there is a single reality. The act of observation does not just reveal reality, it helps to create it. This inherent fuzziness of the quantum world leads to another of its pillars, the uncertainty principle, formulated by the German physicist Werner Heisenberg. This principle states that there is a fundamental, built-in limit to how precisely we can know certain pairs of a particle's properties at the same time. The classic example is position and momentum. The more precisely you manage to measure a particle's position, the less precisely you can possibly know its momentum, its speed, and direction. And the more precisely you measure its momentum, the fuzzier its position becomes. This is not a limitation of our measuring instruments. You could not build a better, more precise machine to get around this problem. It is a fundamental property of nature itself. A particle simply does not possess a perfectly precise position and a perfectly precise momentum at the same time. There is an intrinsic trade-off, a cosmic dance between what can be known and what must remain uncertain. This principle has a mind-bending consequence for the nature of empty space. On the very smallest of scales, the so-called Planck scale, the uncertainty principle allows for a strange kind of borrowing. For incredibly short amounts of time, particles and their antimatter counterparts can borrow energy from the vacuum, popping into existence from literally nothing, before colliding and annihilating each other, paying back the energy debt. The vacuum of empty space, therefore, is not empty at all. It is a roiling, chaotic, and effervescent sea of these virtual particles, a quantum foam of fleeting existence. The solid, predictable, and logical world that we experience every day is, in a very real sense, a grand illusion. It is a classical reality that emerges from this bizarre, probabilistic, and deeply strange quantum foundation. The laws of cause and effect, the solidity of the chair you are sitting on, the very notion that an object can only be in one place at one time, all of these are approximations that work beautifully on our large scale, but they are built upon a bedrock of uncertainty and potential. The final frontier, it turns out, is not only in the unimaginable distances of the cosmos, but also in the infinitesimal spaces within every atom. From the quantum foam at the bottom to the cosmic web at the top, our journey has spanned all of existence. But what is the one, mysterious tool that allows us to even begin to comprehend any of this? How far have we gone in understanding the most complex and enigmatic object we know of? Our own conscious mind. Think, for a moment, about the color red. Not the word red, spelled R-E-D. Not the physical phenomenon of light with a wavelength of approximately 700 nanometers. Think about your actual, subjective, private experience of seeing the color red. The feeling of it. The brilliant crimson of a sunset. The deep garnet of a glass of wine. The bright scarlet of a rose. Where is that experience located? Is it in the photons of light? Is it in the electrical signals traveling from your retina up your optic nerve? Is it in the firing of specific neurons in your visual cortex? Or is it something else entirely? What is it made of? How can a collection of mindless, physical particles, like atoms and neurons, shuffling around in the dark confines of your skull, give rise to the rich, vibrant, and utterly private universe of your own subjective experience? This is the final frontier, and it may be the greatest mystery of them all. Let us now close our eyes, not to sleep, but to observe. Turn your attention inward to the silent, ever-present stream of your own awareness. Notice the effortless flow of thoughts, the way one idea seems to bubble up from nowhere and lead to another. Conjure a memory, the face of a loved one, the feeling of sunlight on your skin from a summer long past, the melody of a favorite song. Feel the gentle sensation of the air in the room, the faint pressure of the clothes against your skin, the simple, profound, and undeniable fact of your own existence. You are here. You are aware. This inner world is the most familiar thing you will ever know. It is the lens through which you have experienced every joy, every sorrow, every moment of your entire life. And yet, scientifically, it is the most mysterious and intractable problem in the universe. It is the great, unanswered question of consciousness. We are each of us a ghost in the machine. This profound mystery is what the philosopher David Chalmers has famously termed the hard problem of consciousness. The easy problems, he says, are not actually easy at all, but they are at least solvable in principle by the methods of neuroscience. These are the problems of explaining the brain's functions, how it can process sensory information, how it focuses attention, how it controls behavior, how it stores and retrieves memories. We are making incredible progress on these fronts, mapping the intricate neural circuits that correspond to these abilities. But the hard problem is of a fundamentally different character. It is the question of why and how any of this physical, objective, third-person processing in the brain should give rise to subjective, qualitative, first-person experience. What scientists call qualia. Why is it like something to be you? Why is it not all just dark inside? Why does all that complex information processing not just happen in the background, like the processes running on your computer, without any inner movie, any subjective feeling at all? This is the explanatory gap that, so far, no scientific theory has been able to cross. That is not for a lack of trying. There are several fascinating and creative scientific approaches that attempt to grapple with this mystery. One is the integrated information theory, or IIT. It proposes that consciousness is not something exclusive to biological brains, but is a fundamental property of any system that has a certain kind of complexity. Specifically, it suggests that consciousness corresponds to a system's capacity to integrate a large amount of information. A system is conscious if its whole is more than the sum of its parts, if it has a rich web of interconnected, causal relationships. Under this theory, any system, whether it is a brain, a sophisticated computer, or perhaps even something as strange as a star, could have some degree of consciousness if it has a high enough level of integrated information. Another leading idea is the global workspace theory, or GWT. This theory uses the metaphor of a theatre. Your brain is a collection of countless unconscious specialist processors, all working in the dark. Consciousness, in this view, is like the bright, shining stage of the theatre. When a piece of information from one of these specialists becomes important enough, it is broadcast onto this global workspace, this stage, making it available to all the other specialists. The content of your consciousness, the thing you are aware of from moment to moment, is whatever happens to be on that stage, under that spotlight. But even these brilliant theories, for all their power in explaining the functions of awareness, do not yet touch the central mystery. They do not explain how the light on the stage becomes a feeling. They do not explain how integrated information feels like the color red. All of our incredible journeys into the universe, from our pale blue dot to the cosmic web, from the quantum foam to the heliopause, have been undertaken with this one indispensable tool. Consciousness is the instrument that conceives of the questions, that designs the experiments, that feels the awe and the wonder at the answers. We are, as the great Carl Sagan once said, the universe's way of knowing itself. The ultimate exploration, then, may not be of distant galaxies, but of the very nature of the awareness that allows us to look up at them and wonder in the first place. The final frontier is not out there, but in here. After this grand tour of everything we know, from the infinitesimally small to the unimaginably large, from the beginning of time to the edge of space, and into the very core of our own minds, we are left with one final, lingering, and perhaps unanswerable question. With hundreds of billions of stars in our galaxy alone, and with perhaps 2 trillion galaxies in the observable universe, many of them ancient and vast, and with the discovery that planets are not the exception but the rule, with countless worlds orbiting in the gentle, life-giving warmth of their parent stars. Where is everybody? This is the question that haunts our search for our place in the cosmos. It is known as the Fermi paradox, and it is, in its simplest form, the profound and deafening silence of the universe. If the universe is teeming with life, and if intelligence is a common outcome of that life, then the sky should be filled with the signs of civilization. But it is not. Let us go outside, on this final step of our journey, and simply gaze up at the night sky. Each one of those twinkling points of light is a sun, a potential anchor for a family of worlds. Many of them are billions of years older than our own star. Life on any of their planets would have had a head start of eons. In that time, a civilization could have grown, developed, and spread, filling the galaxy. We should see the signs of their great engineering projects, so-called astroengineering, like Dyson spheres built to capture the energy of their star. We should see the light from their starfaring empires. The galaxy should be a bustling, noisy, and vibrant place. Our radio telescopes, which have been patiently listening to the heavens for decades, should be overflowing with their messages, their art, their encyclopedias, their simple, friendly hellos. But we have found nothing. When we listen to the universe, all we hear is the whisper of pulsars, the hiss of the cosmic background, the random static of the natural world. There are no messages. There are no beacons. There is only a deep, profound, and perhaps terrifying silence. The Fermi paradox is this stark and unsettling contradiction between the high probability that extraterrestrial intelligence should exist and the utter lack of any evidence for it. Scientists and philosophers have proposed many possible solutions to this great silence, many of them deeply sobering. These potential solutions are often framed as great filters. A filter is some barrier, some challenge that is incredibly difficult for life to overcome. Perhaps the filter is behind us. Perhaps the origin of life itself is an astronomically rare event. Or perhaps the leap from simple microbial life to complex, multicellular life like animals and plants is the filter. This would mean we are one of the very first, or perhaps the only, intelligent species to have ever arisen in our galaxy. This is the rare Earth hypothesis, a solution that would make us both incredibly special and incredibly lonely. But a more chilling possibility is that the great filter lies ahead of us. Perhaps life and intelligence are common, but perhaps it is the nature of all intelligent civilizations to eventually discover a technology that inevitably leads to their own self-destruction. Nuclear war, runaway climate change, a misengineered pandemic, and out-of-control artificial intelligence. In this scenario, the silence of the galaxy is a warning. The graveyards of the cosmos are filled with the silent ruins of civilizations that reached our level of technological sophistication and failed to pass the test. Of course, there are other, less grim possibilities. Perhaps the silence is not a sign of absence, but a sign of something else. Perhaps advanced civilizations are here, but they are hiding, operating under a prime directive not to interfere with young, emerging species like ours. Perhaps their consciousness and their technology are so advanced that we are simply incapable of perceiving them, like an ant colony on the ground, being unaware of the human internet that buzzes all around it. Or perhaps the solution is a simpler, more mundane one. Perhaps the distances between the stars are just too vast. Perhaps interstellar travel, even for a highly advanced civilization, is simply too difficult, too expensive, or too slow to be worth the effort. The silence, in this case, would not be because the universe is empty, but because it is too big. The galaxy could be full of living, thinking civilizations, each of them confined to their own solar system, each of them looking up at their night sky and wondering, just as we are, where is everybody? And so, here we stand, on our pale blue dot, looking out into the vast, silent cosmos. Our long journey tonight has shown us how far we have truly gone. We have sent our machines and our minds from our home world to the edge of the observable universe. We have journeyed inward, to the bizarre foundations of reality itself. And in doing so, we have discovered that the universe is more vast, more strange, and more beautiful than our ancestors could have ever dreamed. But this journey has also shown us how much we do not know. The great silence of the universe is a perfect mirror for the great mystery of our own consciousness. We do not know if we are alone, and we do not know what we are. Perhaps then, our ultimate purpose is not to find all the answers. Perhaps our purpose is to be the part of the universe that asks the questions. In this vast and silent cosmos, perhaps we are the ones who create the meaning. The final frontier, then, is not a place we can ever arrive at. It is the perpetual, hopeful, and beautiful act of reaching, of wondering, of seeking. And our journey has only just begun. Thank you for joining me on this long and gentle exploration tonight. I hope it has brought you some peace, some wonder, and perhaps a comfortable drift into sleep. Until we meet again, for our next journey, I wish you a peaceful and restful night.